An Exploration of Magnetic Fields Through Auroras by Andrea Santa Cruz, Kelly Smith, and Victoria Hunt.
One reason magnetic field research is significant is because it expands our knowledge of possible geomagnetic reversals. A geomagnetic reversal occurs when the magnetic poles switch, and it has been about 780,000 years since the last one. The result of the flip, depicted on the left, does not present the main concern, rather the process of the flip as depicted on the right. The weakening of our protective magnetic field has opened the reversal debate. The media sells the idea that we are entering the beginning of a reversal period, while the scientific community has expressed no concern as the field has not yet dropped to all-time average levels. However, both sides agree that the field is losing strength, exposing us to solar winds that bring auroras and harm, while potential changes in the field lines present their own challenges. Some potential consequences of a geomagnetic reversal is throwing off animals that use magnetic field lines to navigate, such as bees and birds. This would be devastating to countries like the United States because bees are our main pollinators. In addition, communication technology and navigation technology could also be skewed. Also, compass navigation would be impossible during this time because the field lines are not consistent and there would be no true magnetic north. The basics of magnetism. Magnetism is the force of attraction or repulsion of charged particles. In the top image, a normal bar magnet is shown with its field lines drawn. In the bottom left image, two opposite poles are attracted to each other. In the bottom right image, two similar poles repel each other. An important equation to remember when considering magnetism is the Lorentz force equation, F equals QV times B. F represents the force, Q the charge of the particle, B the velocity of particles, and B the magnetic flux density, or the amount of magnetic field lines per unit area. And now Kelly will help us learn more about this subject. Yay!
So one simple way to identify the direction of the components in the Lorentz rule is through the equation F equals QVB and what's known as the thumb rule. So in the thumb rule, you take your right hand for a positive charge and your left hand for a negative charge. And then your thumb can represent the direction of force, your velocity is represented by your pointer finger, and your middle finger shows the magnetic field line direction. And so in order to find one of the three, you will take the other two and point it in the direction given, whether that be north, south, east, and then you just orientate your hand, not your fingers, your hand, depending on whichever direction they give you. So we're going to work out a problem using the Lorentz rule, and the problem is an electron is moving to the east at a speed of 1.8 times 10 to the 5th meters per second. It feels a force in the upward direction with a magnitude of 2.2 times 10 to the negative 12th newtons. What is the magnitude and direction of the magnetic field this electron just passed through? So in order to solve this, we're going to start with the magnitude. You can use the Lorentz rule, which states FB equals QV sine theta. And the reason that it's sine theta is because it's at an angle. And so in order to find all of your components, you can take F, which is given to you in the problem, and V is also given to you in the problem. Because it's an electron, Q is a constant, and then due to the velocity being at a perpendicular to the field, theta is equal to 90 degrees and sine theta is equal to 1. So using this, we can solve for B. In order to solve for B, we have to derive an equation. So you take the Lorentz rule given, and you derive an equation for B, which all you have to do is take FB and divide it by QV sine theta. And then after that, you plug in your given values in this equation, and you end up with 7.6 Teslas. Okay, and then for direction. So previously we learned about the thumb rule, and we can again use this to find direction in this case. But because the charge is negative, you're going to use your left hand. So velocity, which is your pointer finger, is east, so you point it right. The force is north, so you point it up. And as a result, your middle finger points downwards, which means that it's south. And now you can relate all of these principles into our physics of magnetism.
Earth's magnetic field is like a bar magnet, where the southern magnetic pole is at the north geographic location of the Earth, and vice versa. As you can see, the Earth's magnetic field lines loop around from the bottom all the way to the top of the Earth. Their shape, which is like an ellipse, is influenced by the shape of the Earth and the rotational axis of the Earth. The magnetic field lines of the Earth have great influence and power on the electrons, protons, and other particles within the Earth's atmosphere. The purple squiggly line represents the traveling path of the particles. As you can see, the particles spin around the magnetic field lines and accelerate as they approach the Earth. The trajectory of the magnetic field lines demonstrates the location of the mirror points. The mirror points are located at similar latitudes in their respective hemisphere. At these points, the particles have high velocities, energy levels, and compaction rates, which yield the Van Allen radiation belts. This diagram depicts Earth at the center, surrounded by its distorted magnetic field lines. The magnetic field acts as a protective shield from the solar wind of the sun. However, in order for auroras to occur, the particles must enter the Earth's atmosphere. This occurs when the magnetic fields of the Earth and Sun line up perfectly and create a point of weakness through destructive interference. At this point, the tail of Earth's magnetic field becomes stretched and the Sun's solar wind particles fill it in. As more particles fill the tail, it becomes increasingly unstable until it snaps, and the particles accelerate towards Earth along the magnetic field lines discussed in the previous slide. The particles' entrance into the atmosphere causes them to become excited, but it is their return to their stable state, along with interactions from Earth's gases, which causes them to emit visible light to create the aurora.
One major application of Earth's magnetism is the aurora. The aurora history dates back to cave paintings in ancient France. This illustrates its significance as it was used during ancient times. Scientists and philosophers such as Galileo and Aristotle also used this during their research. Even in superstitious times, tribes and civilizations would use auroras as signals of war and destruction. The image shown depicts a cave painting of an aurora in the top right-hand corner. Some of the most admired features of the auroras are their color and shape. For example, the colors are caused by excitation of oxygen and nitrogen gas. High energy excitation results in green lights, while low energy results in red. Nitrogen generally emits blue, while purples, pinks, and whites occur from blending. The shape, however, is more of a scientific mystery. Research continues to be done today on the source. However, scientists predict that it has something to do with electron origin, the gain of energy, and the eventual entrance into the atmosphere. The location of auroras is depicted in the diagram. As shown, auroras generally occur at the northern and southern latitudes, and they are not prevalent near the equator or the middle latitudes. This generally follows Earth's magnetic field lines. In conclusion, the relationships depicted indicate a global phenomenon. Understanding auroras would allow us not only to gain insight into magnetic reversals, but also the distorted implications on satellite, mobile, and compass technology. And this knowledge would ultimately aid in finding a solution to save the Earth from its future imbalances. This is the work cited. This presentation has been brought to you by Kaylee Smith, Andrea Santa Cruz, and Victoria Hunt. Thank you.